Let's continue to do some examples that involve L'Hopital's rule. Our first one is this limit as x approaches 1 of x to the 18th minus 1 divided by x to the 17th minus 1. So if you plug in 1 directly, you're just going to get 1 minus 1, which is 0, over 1 minus 1, which is 0. So applying L'Hopital's rule, we get the same limit, but we take the derivative of the top. So 18 x to the 17th over 17 x to the 16th. So what I need to warn you now is don't over derive. So a very common mistake is to keep taking derivatives and not stop. Now, in the case that x is going to infinity, that usually doesn't hurt you, but in the case where x is going to a number, you can over derive. So if I took the derivative again here, I would get 18 times 17 and 17 times 16 and so on and so forth. But I don't have to. At each step, you can check to see whether or not you can stop. If I plug in 1 for x here, I just get 18 over 17, and that's it. So you can stop. So that's a very common mistake that happens. Don't let that happen to yourself. The next one is also a similar case. Now, you may remember from doing these types of problems that, these things have the same, they have the same degree, so it should just be 5 over 6, which is true. But let's try to do this using L'Hopital's rule. If you plug in infinity here, you're going to see this thing shoots off to positive infinity, this thing shoots off to positive infinity, so you have an infinity over infinity indeterminate form. So by applying L'Hopital's rule, we get the limit as x approaches infinity of 15x squared minus 9 over 18x squared. Okay, so then if I try to examine this again, this still shoots off to infinity, this still shoots off to infinity, so we have to keep going. This is the limit as x approaches infinity of 30x over 36x. Well, in this case, as the x's will cancel, getting us 30 over 36, which reduces to 5 over 6. So this is an example of where L'Hopital's rule is useful and it's great as a self-check, but you really didn't have to use it. So don't feel the need to use it just because you have to. The whole point of tools in your kit is that you use the right one for the job. There's no need, the old adage of Michelangelo painting your house, right? You could hire him to do that, but why involve it if you don't have to? On this one, though, we're going to have to. So as x goes to infinity here, what we see is x cubed, it just shoots off to infinity, and e to the x, even e to the x over 3, as x goes to infinity, it doesn't matter that it's being divided by 3, it still shoots way off to infinity. So what I'm really trying to figure out for this type of problem is which one gets to infinity faster. I know that seems a weird question to ask, but that's really what you're asking with these ratios. They're both racing to infinity. Is the numerator winning or is the denominator winning? Or do they actually end up kind of tying at some proportional rate? So if you can figure out if one is racing at a proportional rate faster or if one's beating the other, that's really your cases for these sorts of things. That's kind of a motivation. For those of you who might be studying things like computer science, one of the big things that you study in computer science is the idea of order of growth. And you determine how quickly algorithms kind of spiral out of control. They, how much computing time, what the time complexity of an algorithm is. And what you're really doing is using these types of techniques to say, all right, is this thing going to spiral out so much that if I use it on large data sets, it just becomes impossible to compute? Or can I make it better? And so this is really kind of a big issue in computer science. So I'm kind of off on a tangent here, but I'm trying to motivate you that there's a real world practice for why you would want to study this type of stuff. So anyway, it's an indeterminate form, infinity over infinity, so let's take a derivative. You're going to get the limit as x approaches infinity of 3x squared 5e to the x over 3 times the derivative of x over 3, which is 1/3. Alright, so now this thing, if I take it to infinity, I still get infinity on top, still get infinity on bottom. So let's just keep rolling. 6x, x over 3, and I generate another 1/3 because this thing generates another 1/3 multiplied by the one you already have. Alright, let's take a look. Still goes to infinity, still goes to infinity. Let's keep going. So the limit as x goes to infinity, 6. Okay, now in this case, this is a constant, but this still shoots off to infinity. 0. So what that tells me is that the e function grows way, way more quickly than the x cubed function does. It dwarfs it. And that kind of makes sense because at some point for some x value, x cubed is whatever. So like, you know, if you take a calculator and you plug in 100 cubed, right, you get 1,000,000. But if you put e to the 100 over 3, so basically like e to the 33-ish, you take e to the 33 and plug that in the calculator, it's a big number. Way bigger. It's going to be a lot bigger than 1,000,000. I don't know that, but I mean, shit, I'd bet a lot of money. It's way, way, way bigger than 1,000,000. And that gets nastier even as you get, you know, once x becomes 1,000,000, that number becomes crazy large. And so I'm saying all that to say that the study of order growth is a very important thing in the study of mathematics, but specifically in the study of computer science. So you use that lens to kind of focus why we're doing this, and hopefully that'll help kind of rein you in as to why this is important to study.